There's something hauntingly beautiful about the way a star dies. Picture this: a brilliant, massive star, burning fiercely for millions of years, suddenly collapsing in on itself in a cataclysmic explosion so powerful it outshines entire galaxies. And yet, in that violent end, something extraordinary begins. The remnants of that star, scattered across the cosmos, become the building blocks of everything we know. The very atoms in your body, the ground beneath your feet, even the air you breathe. It's a paradox as old as time itself, destruction giving birth to creation. When you look up at the night sky, those twinkling lights aren't just distant suns. They're part of an endless cycle of life and death. Some of those pinpricks of light are already gone, their light taking centuries to reach us, their stories written in the echoes of their final moments. Supernova, neutron stars, even the enigmatic black holes, they're all chapters in the same cosmic saga. These celestial ghosts don't just vanish, they transform. Their ashes become the raw materials for new stars, new planets, and ultimately, new life. It's a story of resurrection written in the fabric of the universe. So what happens when a star dies, and how does its death pave the way for something new? This isn't just about distant, abstract phenomena, it's about our origins. Every element heavier than hydrogen and helium, from the carbon in your bones to the iron in your blood, was forged in the heart of a dying star. Without these stellar graveyards, the universe as we know it wouldn't exist. Over the next few minutes, we'll unravel the mysteries of these cosmic alchemists, exploring how their explosive ends create the very ingredients of life. From the dazzling fury of supernova to the eerie quiet of neutron stars, we'll journey through the afterlife of stars and discover how their echoes shape everything around us. The story of a star begins in darkness, not the emptiness of space, but a dense, swirling cloud of gas and dust drifting silently through the cosmos. Gravity pulls these particles together, tightening the cloud into a spinning disk. As pressure builds, temperatures soar, until the core becomes so hot and dense that hydrogen atoms collide, fusing into helium in a burst of light and energy. And just like that, a star is born. For smaller stars like our Sun, this peaceful glow can last for billions of years, a steady beacon in the cosmic dark. But for the giants, those many times more massive, their lives burn brighter and end far sooner, setting the stage for something truly extraordinary. When a star exhausts its fuel, gravity takes over once more, crushing the core with unimaginable force. For smaller stars, this collapse halts at a certain point, leaving behind a smoldering ember called a white dwarf, a dense, Earth-sized remnant that slowly cools over eons. But for massive stars, the collapse doesn't stop. The core implodes in an instant, triggering a shockwave so powerful it blasts the star's outer layers into space in a supernova, a flash of light so intense it can outshine entire galaxies. In that explosion, temperatures reach staggering heights, forging elements like gold, uranium, and iron, elements that would never form in the quiet heart of an ordinary star. And here's the miracle: that explosion isn't just an end. It's a scattering of stardust, a cosmic sowing of seeds. The debris from these violent deaths drifts through space, mingling with other clouds of gas and dust until gravity pulls them together once more. Some of that material becomes new stars, some becomes planets, and some, like the calcium in your bones or the oxygen you breathe, becomes part of you. Every time you look at the night sky, you're not just seeing distant suns, you're seeing the past, present, and future of the universe itself, written in the life and death of stars. There's nothing in the universe quite as spectacular or as destructive as a supernova. Imagine a star 20 times more massive than our Sun, burning through its fuel in a fiery blaze that lasts millions of years. But when that fuel runs out, gravity doesn't just gently pull it inward. No, this collapse happens in seconds. The star's core, no longer able to resist its own weight, crushes down with such force that protons and electrons merge, forming neutrons in a single, unimaginably dense ball. And then it rebounds. The energy released in that instant sends a shockwave ripping outward, tearing the star apart in an explosion so bright it can outshine a galaxy. For weeks, even months, that dying star blazes with the light of billions of suns, scattering its guts across light years of space. But hidden in that destruction is something miraculous. The extreme heat and pressure inside a supernova act like a cosmic forge, smashing atoms together to create elements heavier than iron, elements like gold, platinum, and uranium that simply can't form in the quiet heart of an ordinary star. Every time you hold a piece of jewelry or glance at a watch, you're holding stardust forged in one of these violent deaths, and the story doesn't end there. The shockwave from a supernova doesn't just vanish. It slams into nearby clouds of gas and dust, compressing them so tightly that new stars begin to form. It's as if the universe itself recycles, turning death into life on a scale we can barely comprehend. Some of those new stars will eventually explode too, scattering even more heavy elements into the void. Over billions of years, this cycle repeats, enriching the cosmos with the building blocks of planets, oceans, and even life itself. But supernovae aren't just creators, they are also messengers. Because they shine so brightly, astronomers use them as cosmic mile markers, measuring vast distances across the universe. And when we look at the light from ancient supernova, we're glimpsing the universe as it was billions of years ago, watching the very elements that would one day make up our world being flung into space. It's a reminder that we're not just observers of the cosmos, we're part of its story, made from the ashes of stars that died long before our sun was born. If a supernova is the universe's grand finale, then a neutron star is its encore, an encore so bizarre it defies everything we know about physics. Picture the core of a massive star, crushed down to the size of a city, yet weighing more than our sun. The gravity here is so intense that atoms themselves collapse, squeezing protons and electrons together until they merge into neutrons. The result, a single teaspoon of neutron star material would weigh 1 billion tons on Earth. Its matter pushed to its absolute limit, a form so dense it's essentially a single, gigantic atomic nucleus spinning in the void. And spin they do. Some neutron stars rotate hundreds of times per second, their surfaces moving at nearly 1/4 the speed of light. These rapid spinning stars, called pulsars, act like cosmic lighthouses, beaming radiation across the galaxy in precise, clockwork pulses. When astronomers first detected these signals in the 1960s, they were so regular that some wondered if they were picking up transmissions from an alien civilization. But the truth was even stranger. Nature itself had built these perfect cosmic timekeepers from the wreckage of a dead star. Yet neutron stars aren't just fascinating oddities, they're cosmic laboratories. The pressures inside them are so extreme that matter behaves in ways we can't replicate on Earth. Atoms are packed so tightly that they form exotic states, like nuclear pasta, layers of materials so dense they resemble spaghetti or lasagna sheets under a microscope. Even time and space warp around them. If you could stand on the surface of a neutron star, the gravity would be so strong that light itself would bend, distorting your view of the universe into a swirling, funhouse mirror. But perhaps the most astonishing thing about neutron stars is how they shape the cosmos. When two of these ultra-dense objects collide, the explosion ripples through space-time as gravitational waves, while also spraying gold, platinum, and other heavy elements across the galaxy. In fact, most of the precious metals on Earth likely came from neutron star collisions billions of years ago. So the next time you hold a wedding ring or a silver coin, remember, you're holding debris from one of the most violent and beautiful events in the universe. These stellar remnants are more than just relics of destruction. They're proof that even in death, stars continue to shape the universe, forging the elements that make life possible and pushing the boundaries of physics itself. And as we study their pulses, their collisions, and their impossible density, we're not just learning about the fate of stars, we're uncovering the secrets of matter itself. Black holes are where the universe bends the rules beyond recognition. Imagine the aftermath of a supernova so colossal that not even a neutron star remains, just an infinitely dense point where gravity becomes unbeatable. Not even light, the fastest thing in existence, can escape its pull once it crosses the event horizon, that invisible boundary marking the point of no return. This isn't just a cosmic vacuum cleaner, though. A black hole is more like a tear in the fabric of space-time itself, warping everything around it in ways that challenge our understanding of physics. What happens inside a black hole? The truth is, we don't know for sure. The laws of physics as we understand them break down under such extreme conditions. Matter isn't just crushed, it's compressed into a singularity, a point of infinite density where time and space cease to behave normally. Some theories suggest it might tunnel into another universe or create a wormhole, a shortcut through the cosmos. Others propose it simply vanishes from existence as we know it. The mystery is part of what makes black holes so fascinating. They're the universe's ultimate puzzles, defying explanation while shaping everything around them. But black holes aren't just destructive forces. Their gravity is so immense that they act as anchors for entire galaxies, including our own Milky Way. At the center of nearly every large galaxy, there's a supermassive black hole, millions or even billions of times heavier than our Sun. These cosmic giants don't just sit there silently, they actively shape their surroundings. As matter spirals into them, it heats up to incredible temperatures, glowing brightly as quasars, some of the most luminous objects in the universe. The energy they release can regulate star formation, either triggering bursts of new stars or suppressing them entirely. Without black holes, galaxies might not have the structure needed to foster stable solar systems like ours. And then there's the drama of black hole mergers. When two of these gravitational monsters collide, they send ripples through space-time itself, gravitational waves that stretch and compress the fabric of the cosmos as they travel. These waves were first detected in 2015, confirming a prediction Einstein made a century earlier. Each merger is a cataclysmic event, releasing more energy in seconds than all the stars in the observable universe combined. Yet even in these violent encounters, black holes create. The heavier elements forged in their swirling disks, the way they fling matter across space, these processes seed the universe with the raw materials for new stars, planets, and even life. So while black holes might seem like cosmic monsters, they're also architects. They sculpt galaxies, power quasars, and generate the very elements that make up our world. Their existence reminds us that the universe isn't just a place of order and predictability. It's a dynamic, ever-changing arena where the most extreme phenomena can give rise to the conditions we call home. And as we continue to study them, we're not just uncovering the secrets of these dark giants, we're piecing together the story of how everything, including us, came to be. While supernova and neutron stars steal the cosmic spotlight with their dramatic endings, there's a quieter, gentler fate awaiting stars like our Sun, one that's no less profound. Picture a star not massive enough to explode, but too stubborn to fade without a trace. As it exhausts its nuclear fuel, it doesn't collapse in a violent burst. Instead, it swells into a red giant, puffing away its outer layers in a slow, shimmering exhale. What remains isn't a smoldering crater or a gravitational abyss, but a glowing ember no larger than Earth, a white dwarf. At first glance, a white dwarf might seem unremarkable compared to its flashy stellar cousins, but don't let its size fool you. This tiny remnant packs the mass of a star into a volume a million times smaller, making it so dense that a sugar cube-sized chunk would weigh as much as an elephant. And here's the twist: it doesn't burn or fuse elements anymore. It just glows, radiating leftover heat like a cosmic hot coal, gradually cooling over trillions of years until it fades into darkness as a black dwarf, a cold, invisible relic of a star that once was. Yet before it dims forever, a white dwarf gives the universe one last gift. As it sheds its outer layers, it doesn't just vanish quietly. Those expelled gases form intricate, glowing shells called planetary nebulae, misnamed centuries ago because their round shapes reminded early astronomers of planets. But these aren't just pretty cosmic decorations. Within those swirling clouds lies a treasure trove of carbon, oxygen, and other life-giving elements, all forged in the star's final act. Every breath you take contains oxygen atoms that might have once been part of a dying star's farewell, and the story gets even more fascinating. Some white dwarfs aren't content to fade alone. If they orbit another star, they can siphon material from their companion, reigniting nuclear reactions on their surface in sudden, brilliant flashes called nova. In extreme cases, they might even gorge themselves until they cross a critical threshold, detonating in a type of supernova that scatters iron and silicon across the galaxy. It's a reminder that even the quietest stars can have dramatic endings, and that their remnants play a vital role in seeding the cosmos with the ingredients for new worlds. So while white dwarfs may not have the explosive flair of supernova or the mind-bending physics of neutron stars, they're just as crucial to the cosmic cycle. They're the universe's recyclers, turning the ashes of sun-like stars into the building blocks of planets, oceans, and life itself. And as they cool into darkness over eons, they leave behind a legacy written not in fire, but in the silent, steady enrichment of the cosmos. Planetary nebulae are the universe's way of turning death into art. When a star like our Sun reaches the end of its life, it doesn't just fade away, it transforms, shedding its outer layers in a final, breathtaking display. These glowing shells of gas and dust, illuminated by the star's exposed core, paint the cosmos with shapes so intricate they look like they were crafted by an unseen hand. Some resemble delicate butterflies, their wings unfurled across light years of space. Others twist into spirals or stretch into hourglass figures, as if the star itself is marking the passage of time. And though they're called planetary nebulae, they have nothing to do with planets, a misnomer from centuries ago when astronomers peering through early telescopes mistook their round shapes for distant worlds. What makes these cosmic masterpieces even more remarkable is what they leave behind. As the dying star expels its outer layers, it releases a rich cocktail of elements, oxygen, nitrogen, carbon, into the void. These aren't just random chemicals, they're the building blocks of life itself. The oxygen we breathe, the nitrogen in our DNA, even the carbon that forms the backbone of every organic molecule on Earth. All of it was forged in the hearts of stars and scattered across the galaxy by nebulae like these. It's a poetic cycle. The death of one star becomes the raw material for new stars, new planets, and perhaps even new life. But how does a star create something so stunning in its final moments? The process begins when a sun-like star exhausts its nuclear fuel. No longer able to resist gravity's pull, its core contracts, heating up so intensely that it pushes the outer layers outward in a slow, shimmering wind. Over thousands of years, this wind carves the gas into intricate structures, while the dying star's ultraviolet radiation lights it up like a neon sign in the cosmic dark. Some nebulae glow in vivid reds and blues, the colors revealing their chemical makeup. Oxygen shines green, hydrogen burns red, and nitrogen adds delicate purple hues. It's a celestial light show that can last for tens of thousands of years before fading into the darkness. And here's the twist: the star's core remains behind as a white dwarf, a dense ember that slowly cools over eons. But before it vanishes into obscurity, it acts like a cosmic flashlight, illuminating the very nebula it created. This interplay between the white dwarf and its expelled layers creates some of the most symmetrical and awe-inspiring shapes in the universe. Take the Ring Nebula, for example, a perfect smoke ring of glowing gas, so precise it looks like it was drawn with a compass. Or the Helix Nebula, nicknamed the Eye of God, its eerie glow peering out from the depths of space. These structures aren't just beautiful, they're also teaching astronomers how stars recycle their material, enriching the galaxy with each graceful death. So the next time you gaze up at the night sky, remember, those distant stars aren't just points of light. They're future artists waiting to paint their final masterpieces across the cosmos. And when their time comes, they won't just vanish, they'll transform, leaving behind a legacy of beauty and the very elements that make our existence possible. Planetary nebulae remind us that even in death, stars give birth to something new, weaving their stories into the fabric of the universe itself. Every atom in your body that isn't hydrogen, the carbon in your cells, the calcium in your bones, even the iron in your blood, was forged in the heart of a star. Think about that for a moment. The oxygen you're breathing right now was once part of a celestial furnace, fused under unimaginable pressure and heat before being flung into the cosmos by a dying star's final act. This isn't poetic exaggeration, it's science. The universe began with only the lightest elements, hydrogen and helium, scattered like cosmic confetti after the Big Bang. Everything else, every heavier element that makes up the world around us, had to be cooked up inside stars. Take carbon, for example. It's the backbone of life, the element that forms the intricate chains of our DNA, the sugars in our food, even the graphite in your pencil. But carbon doesn't just appear out of nowhere. Inside a star, helium atoms collide under crushing pressure, fusing into beryllium, and then, when another helium atom slams into it, carbon is born. This process, called the triple alpha reaction, happens in the cores of stars like our Sun during their quieter, middle-aged years. But for elements heavier than carbon, stars have to work even harder. Oxygen, neon, magnesium, these are forged in the final, desperate stages of a star's life, as it burns through its fuel and begins to collapse. Then there are the real heavyweights elements like gold, platinum, and uranium. These aren't made in the gentle simmer of a living star. No, they require something far more violent, the cataclysmic explosion of a supernova or the collision of two neutron stars. In those unimaginable moments of destruction, atoms are bombarded with so many neutrons that they rapidly grow heavier, forming elements that would never exist under normal stellar conditions. When two neutron stars spiraled into each other in 2017, The resulting collision didn't just send gravitational waves rippling through the universe, it also produced an entire Earth's worth of gold in seconds. That's right, the ring on your finger, the circuitry in your phone, even the gold reserves in bank vaults were likely born in similar cosmic cataclysms billions of years ago. But how do these elements escape their stellar forges and end up in places like Earth? Supernovae are the universe's ultimate recyclers. When a massive star explodes, it doesn't just vanish, it scatters its enriched guts across light years of space, seeding nearby gas clouds with the raw materials for new stars and planets. Over billions of years, gravity pulls these clouds together, forming fresh generations of stars surrounded by rocky worlds. Our solar system is one such example, a cosmic heir to the remnants of long-dead stars. The iron in Earth's core, the silicon in its rocks, the nitrogen in its atmosphere, all of it was once stardust drifting through the void until gravity gave it a new home. This cycle of creation and destruction isn't just a footnote in astrophysics, it's the reason we're here. Without the death of stars, there would be no planets, no oceans, no life. The calcium in your teeth was once part of a red giant's farewell sigh. The phosphorus in your DNA might have been forged in a supernova's fury. Even the copper in electrical wires traces its origins to the collision of neutron stars. We are quite literally the universe remembering itself, a collection of atoms that once burned in distant suns, now awake and wondering about their own origins. So the next time you look up at the night sky, remember, you're not just a spectator of the cosmos, you're a part of it, woven from the same stardust as the galaxies above. And in a way, those long-dead stars live on, not just in the light that reaches us across the ages, but in every breath you take, every step you make, every beat of your heart. The journey from stardust to planets is one of the universe's most breathtaking transformations. Picture a vast, drifting cloud in space, a cosmic graveyard filled with the remnants of long-dead stars. These aren't just scattered ashes, they're gold, silicon, oxygen, and iron, the very ingredients needed to build new worlds. But how does this debris, flung across light years by supernova and stellar winds, become something as solid as a planet? It starts with gravity, the universe's great architect, pulling these scattered atoms together into dense, cold molecular clouds. Over millions of years, these clouds grow heavier, their cores collapsing under their own weight until the pressure ignites a new star, a protostar, surrounded by a swirling disk of gas and dust. This disk, called a protoplanetary disk, is where the magic happens. Tiny particles of stardust, no bigger than grains of sand, begin to stick together, clumping into larger and larger chunks. At first, it's a slow dance, static electricity and gentle collisions building pebbles, then boulders, then mile-wide planetesimals. But as these objects grow, their gravity strengthens, pulling in more material with increasing speed. In the inner regions of the disk, where temperatures are high, only metals and silicates can survive, forming the rocky cores of planets like Earth. Farther out, where it's cold enough for ices to exist, gas giants like Jupiter take shape, their massive gravity scooping up hydrogen and helium left over from the star's birth. What's astonishing is how much of this process is written into our own planet. The iron in Earth's core that was forged in the heart of a massive star before being scattered by a supernova. The silicon in our rocks, it condensed from the same stellar debris that once floated between the stars. Even the water in our oceans might trace its origins to icy grains that formed in the frigid outer reaches of a protoplanetary disk, later delivered to Earth by comets. Every mountain, every ocean, every grain of sand is a testament to the universe's endless cycle of destruction and rebirth, and it's not just our solar system. Across the galaxy, this same process repeats, with dead stars giving rise to new ones, and their remnants shaping planets we've yet to discover. Some of those worlds might be barren rocks scorched by their suns. Others could be icy moons hiding subsurface oceans. A few might even harbor life, their chemistry built from the same stardust as ours. The universe doesn't waste a single atom. Every explosion, every collision, every quiet whisper of a dying star is part of a grander story, one where the end of one chapter becomes the beginning of the next. So when you stand on solid ground, remember, you're standing on the legacy of stars that shone billions of years ago. The carbon in your cells, the oxygen in your lungs, the very ground beneath your feet, it's all stardust, reshaped by time and gravity into a world that can wonder about its own origins. In a very real sense, we are the universe looking back at itself, a chain of cosmic inheritance stretching back to the first stars that ever burned. Consider this: every living thing on Earth, from the tallest tree to the tiniest microbe, shares a universal ancestry, not just in biology, but in chemistry. The atoms that make up your body didn't originate here. They were crafted in the nuclear furnaces of stars, then scattered across the galaxy by explosions so powerful they defy comprehension. Take carbon, for instance. It's the element that forms the backbone of every organic molecule, the literal foundation of life as we know it. But carbon doesn't just appear out of thin air. It's forged in the hearts of stars like our Sun, where helium atoms collide under immense pressure, fusing into this life-giving element over millions of years. When such stars die, they don't just vanish, they release their carbon into space, where it mingles with interstellar clouds, waiting to become part of something new. Oxygen, another cornerstone of life, follows an even more dramatic path. Most of it isn't made in the quiet glow of a sun-like star, but in the final, fiery throes of massive stars on the brink of collapse. As these giants burn through their fuel, their cores become factories for heavier elements, churning out oxygen atoms that will one day end up in the water we drink and the air we breathe. When these stars finally explode as supernova, they catapult these elements into the void at nearly a tenth the speed of light, seeding nearby nebulae with the raw materials for future planets and eventually living organisms. Iron, too, tells a story of cosmic alchemy. Unlike lighter elements, iron isn't just a byproduct of stellar fusion, it's the end of the line. Stars can't fuse iron into heavier elements without losing energy, so when iron builds up in a star's core, it's a death sentence. The core collapses, triggering a supernova so violent that it creates elements even heavier than iron, like gold and uranium in the process. The iron in your blood, the same element that once heralded a star's demise, now carries oxygen through your veins, a direct link between the life-giving and the celestial. This recycling of stellar material isn't just a one-time event, it's an ongoing process that's shaped the universe for billions of years. The gas and dust clouds where new stars form are constantly being enriched by the remains of their predecessors, each generation of stars adding more complex elements to the cosmic mix. Without this cycle, the universe would still be a sea of hydrogen and helium, devoid of the diversity needed for planets, let alone life. The fact that we exist at all is proof of this grand recycling program, where the death of stars becomes the birth of biology. And it's not just about the elements themselves, but how they come together. In the vast molecular clouds where new stars are born, simple molecules like water, ammonia, and methane form on the surfaces of dust grains, icy remnants of stellar explosions. These molecules, delivered to young planets by comets and asteroids, become the precursors to amino acids, the building blocks of proteins. The same carbon that once floated in space as part of a dying star's exhale now forms the intricate structures of DNA, RNA, and every cell in your body. The universe doesn't just create life, it curates it, refining its ingredients over eons until the conditions are just right. So when we look for life beyond Earth, we're not just searching for water or the right temperature. We're following the trail of stardust, seeking out places where this cosmic chemistry has had time to work its magic. Every exoplanet orbiting a distant star, every moon hiding an underground ocean, is a potential testament to this universal recipe. The elements are the same, the story is written in the atoms. And as we piece together how life arose here, we're also learning where else it might exist, tracing the echoes of dead stars across the galaxy. This isn't just science, it's a reminder of our connection to the cosmos. The calcium in your bones was once part of a red giant's farewell. The phosphorus in your DNA might have been forged in the collision of neutron stars. Even the salt in your tears carries remnants of ancient supernova. We are, in the most literal sense, made of stardust, not as a metaphor, but as a fact written into every cell. The universe didn't just create us, it became us, turning the remnants of its most violent events into the quiet miracle of life. And as we continue to explore the cosmos, we're not just uncovering the secrets of the stars, we're discovering our own origins, written in the elements they left behind. Pulsars are the universe's most precise timekeepers, spinning neutron stars so perfectly regular in their pulses that they rival atomic clocks. Imagine a star heavier than our sun, crushed into a ball no wider than a city, rotating hundreds of times per second. As it spins, beams of radiation shoot from its magnetic poles, sweeping across space like a cosmic lighthouse. If Earth happens to lie in the path of those beams, we detect them as rhythmic pulses of radio waves, sometimes as steady as a metronome. The first time astronomers observed this in 1967, they nicknamed the signal Little Green Men 1, half convinced they'd stumbled upon an alien transmission. But the truth was even more extraordinary. Nature had crafted its own celestial beacon, one that would revolutionize our understanding of the cosmos. What makes pulsars so invaluable to science is their unbelievable precision. Some, like the famous millisecond pulsar PSRJ 433+1731, rotate with such consistency that their pulses can be predicted down to microsecond accuracy over decades. This reliability turns them into cosmic tools. Astronomers use them like interstellar GPS, mapping distances across the galaxy by measuring slight delays in their pulses as they pass through interstellar gas. They've even helped test Einstein's theory of general relativity with breathtaking precision. When two pulsars orbit each other, their gravitational waves cause tiny shifts in pulse timing, shifts that match Einstein's predictions almost perfectly. It's as if the universe itself handed us a laboratory to probe the fabric of space-time. But pulsars aren't just scientific instruments, they're also survivors. Planets have been discovered orbiting these extreme objects, worlds that somehow endured the violent supernova that birthed their pulsar parent. Take PSRB 1257+12, a pulsar with at least 3 rocky planets in its grip. These aren't hospitable places, bathed in intense radiation and subject to brutal gravitational tides. They're more like cosmic curiosities. Yet their very existence proves that planetary systems can form or persist in the most hostile environments imaginable. If life could arise anywhere, why not here? Some scientists speculate that microbes might cling to subterranean niches on such worlds, shielded from the lethal rays above. Then there are the Black Widow pulsars, so named because they're slowly vaporizing their stellar companions. These ultra-fast spinning pulsars whip around binary partners, their fierce winds and radiation stripping material from the other star, a process that will eventually consume it entirely. It's a cosmic dance of destruction, yet one that powers some of the most energetic phenomena in the universe. even in their violence, pulsars shape their surroundings, energizing nebulae and lighting up interstellar clouds with their piercing beams. Perhaps the most astonishing thing about pulsars is how they bridge the gap between the predictable and the extreme. Their pulses are so regular they've been proposed as navigation aids for future interstellar travel. Yet their environments are so harsh they defy almost every condition we associate with habitability. They're reminders that the universe doesn't operate in absolutes, that even in the most unforgiving corners of space, nature finds a way to create precision amid chaos. And as we continue to study their rhythmic flashes, we're not just unraveling the secrets of dead stars, we're learning to read the cosmos itself, one pulse at a time. If pulsars are the universe's precision clocks, then magnetars are its cosmic electromagnets, neutron stars with a twist so extreme it defies belief. These rare stellar remnants possess magnetic fields a quadrillion times stronger than Earth's, so intense they could wipe credit cards clean from halfway across the solar system. To put that in perspective, a magnetar's field could rearrange the very atoms in your body from thousands of miles away, twisting electron orbits into impossible shapes. It's as if the laws of physics as we know them start to fray at the edges under such unimaginable forces. What creates such monstrous magnetic fields? The answer lies in the star's violent birth. When a massive star collapses into a neutron star, its already powerful magnetic field gets concentrated into a space no bigger than Manhattan. But in some cases, perhaps due to turbulent motions in the collapsing core or the merging of two neutron stars, that field becomes amplified to ludicrous levels. The result is a celestial powerhouse that makes even the strongest lab magnets look like fridge decorations. The effects of these fields are nothing short of apocalyptic. Magnetars experience starquakes, cracks in their ultra-dense crust caused by magnetic stresses so powerful they ripple through the star like seismic waves. When these quakes occur, they release bursts of gamma rays and X-rays so bright they can briefly outshine the entire Milky Way. In 2004, a magnetar 50,000 light-years away unleashed a flare that ionized Earth's upper atmosphere despite being halfway across the galaxy. That's like lighting a match in New York and feeling its heat in Tokyo. Yet for all their destructive potential, magnetars also offer scientists a unique window into extreme physics. Their environments are so intense that atoms stretch into needle-like shapes, and empty space itself becomes polarized, bending light in ways Einstein never imagined. Some theories suggest their magnetic fields might even create magnetic monopoles, hypothetical particles with a single magnetic pole that could rewrite our understanding of quantum physics. Every time a magnetar flares, it's not just a cosmic light show. It's an experiment in conditions we could never replicate on Earth. Perhaps the most fascinating thing about magnetars is how fleeting they are. Unlike pulsars that spin for millennia, these ultramagnetic monsters fade fast, their fields decaying over just 10,000 years, a blink in cosmic time. That makes them rare cosmic snapshots, temporary windows into the universe's most extreme states. And when they finally go quiet, they leave behind a neutron star that's still dense, still strange, but just a little less monstrous. So while we might never visit a magnetar or harness its power, its existence reminds us that the universe has corners where the ordinary rules don't apply. Places where matter bends to forces we can barely comprehend, and where the fabric of reality itself gets stretched to the breaking point. They're proof that even in death, stars continue to surprise us, pushing the boundaries of what we thought was possible. The aftermath of a supernova is anything but quiet. Long after the initial explosion fades from view, its remnants linger like cosmic ghosts, glowing faintly in X-rays and radio waves across the vastness of space. These expanding shells of gas and dust, hurled outward at thousands of kilometers per second, continue to tell the story of the star's dramatic end for millennia. Take the Crab Nebula, for instance, a sprawling, filament-filled cloud that was once the heart of a massive star. When that star exploded in the year 1054, the light was so bright it could be seen in broad daylight for weeks, recorded by astronomers across China, Japan, and the Middle East. Nearly 1,000 years later, we can still see its aftermath, a glowing testament to the violence and beauty of stellar death. But what keeps these remnants shining long after the explosion? The answer lies in the shockwaves rippling through space, heating interstellar gas to millions of degrees until it emits X-rays. At the heart of the Crab Nebula, a rapidly spinning neutron star, the crushed core of the original star, acts like a cosmic power plant, blasting the surrounding gas with intense radiation and high-speed particles. This energy illuminates the nebula, creating intricate tendrils of light that shift and change over decades, a slow-motion firework still unfolding before our eyes. These remnants aren't just celestial memorials, they're also cosmic architects. As the shockwaves plow through nearby clouds of gas and dust, they compress the material, triggering the birth of new stars. It's a chain reaction of creation and destruction, where one star's death becomes the catalyst for another's beginning. In the Eagle Nebula, for example, shockwaves from ancient supernova likely helped sculpt the iconic pillars of creation, those towering columns of gas where stars are forming right now. The same forces that tear stars apart also lay the groundwork for their successors, and the Crab Nebula is just one example. The Veil Nebula, a wispy remnant in Cygnus, stretches over 100 light-years, its delicate filaments glowing in hues of red and blue as they collide with interstellar gas. Or Cassiopeia A, the leftover wreckage of a star that exploded around the year 1680, its shock waves still racing outward at 15 million kilometers per hour. Each of these remnants tells a different story. Some show the ragged edges of a star torn apart unevenly, while others, like the perfectly spherical shell of G 1.9 plus 0.3, reveal explosions so symmetrical they look almost designed. What's truly remarkable is how long these remnants endure. Unlike the brief, brilliant flash of the supernova itself, their glow can persist for tens of thousands of years, slowly fading as they merge with the interstellar medium. By studying them, astronomers don't just learn about the stars that died, they uncover clues about the universe's chemical evolution. The heavy elements forged in the explosion, oxygen, neon, sulfur, are scattered into space, enriching future generations of stars and planets. Without these stellar graveyards, the cosmos would lack the diversity of elements needed for planets, oceans, or life. So the next time you see an image of a supernova remnant, remember, you're not just looking at a ghost. You're witnessing a cosmic transformer, turning destruction into new possibilities. These glowing remnants are more than just echoes of the past. They're the universe's way of recycling itself, ensuring that every ending is also a beginning. There's a profound rhythm to the universe, a cycle as old as time itself, where endings are never truly final. When a star dies, it doesn't just disappear into the void. Instead, it scatters its essence across the cosmos, a cosmic scattering of seeds that will one day grow into something new. Think of it like a forest fire. The flames may destroy, but they also clear the way for fresh growth, nourishing the soil with ash. In the same way, a supernova's destruction enriches the galaxy, sprinkling space with the heavy elements that will eventually coalesce into new stars, planets, and perhaps even life. This process didn't start with our sun or even the first generation of stars. It began nearly 14 billion years ago, when the Big Bang forged only the simplest elements: hydrogen, helium, and trace amounts of lithium. For the universe to create anything more complex, it needed stars, giant nuclear furnaces capable of smashing atoms together under unimaginable pressure. The first stars, born from pristine gas, were massive and short-lived, burning fiercely before exploding in spectacular supernova. Those explosions seeded the cosmos with carbon, oxygen, and nitrogen, the building blocks of everything that followed. Over eons, each stellar generation added to this cosmic reservoir. A star like our Sun, for example, is a product of at least 2 previous generations of stars. The iron in Earth's core, the silicon in its rocks, even the gold in your jewelry, all of it was forged in the hearts of long-dead stars, then hurled into space by their violent ends. When our solar system formed 4.5 billion years ago, it was from a cloud already rich with these recycled materials. The same stardust that once swirled around ancient supernova now flows through your veins, a reminder that the universe is deeply interconnected. But the cycle doesn't stop there. Right now, in the Orion Nebula, new stars are igniting from the remnants of their predecessors, their protoplanetary disks brimming with the same elements that once made up planets like ours. Some of those disks may already be forming rocky worlds, perhaps even ones with oceans and atmospheres. And in billions of years, when those stars die, they'll return their enriched materials to the void, continuing the cycle anew. What's truly remarkable is how efficient this cosmic recycling program is. Nothing is wasted. Even the gentle death of a sun-like star, quietly shedding its outer layers as a planetary nebula, contributes oxygen and carbon to the interstellar medium. The heaviest elements, like gold and platinum, might take a more dramatic route forged in neutron star collisions or the cores of supernova, but they, too, eventually find their way into new systems. The universe is a master economist, turning every loss into an opportunity for creation. This endless dance of destruction and rebirth isn't just a backdrop to the cosmos, it's the reason we're here. Without the deaths of countless stars, the universe would still be a sea of hydrogen, devoid of the complexity needed for planets or life. Every mountain, every ocean, every living thing is a testament to this grand cycle, a chain of cosmic inheritance stretching back to the first stars. So when you gaze up at the night sky, remember, you're not just looking at distant points of light. You're witnessing a story of resurrection, written in the atoms of the universe itself. That gold necklace you're wearing or the platinum ring on your finger, it wasn't always here on Earth. In fact, these precious metals took an extraordinary journey across the cosmos before ending up in your hands. Unlike lighter elements forged in ordinary stellar furnaces, gold and platinum require something far more extreme: the violent collision of 2 neutron stars. When these incredibly dense stellar corpses spiral into each other, they create a phenomenon called a kilonova, an explosion so powerful it briefly outshines an entire galaxy. In that cataclysmic moment, temperatures reach trillions of degrees, and pressures become so intense that atoms are flooded with neutrons. Ordinary matter can't survive under these conditions. Instead, atomic nuclei rapidly capture these neutrons, growing heavier and heavier until they form elements like gold, platinum, and uranium. The explosion then hurls this newly forged material outward at nearly the speed of light, scattering it across interstellar space like cosmic shrapnel. One such event, observed in 2017, produced an astonishing amount of heavy elements. Scientists estimate that collision alone created about 10 Earth masses worth of gold. But how does this stardust end up on Earth? Over millions of years, these heavy elements mingle with vast clouds of gas and dust drifting through the galaxy. When gravity pulls these clouds together to form new stars and planets, the precious metals become part of the mix. Our solar system likely formed from a nebula enriched by multiple neutron star collisions over billions of years. That's why gold is so rare. It didn't just form anywhere. It required one of the universe's most violent and infrequent events. What's truly remarkable is how recent these discoveries are. For decades, scientists debated where heavy elements came from. Some thought supernova could produce them, while others suspected neutron star mergers. The breakthrough came when astronomers detected gravitational waves from colliding neutron stars in 2017. The accompanying kilonova flare contained clear signatures of heavy elements like gold, finally solving the mystery. Suddenly, every piece of gold jewelry became a tangible link to these cosmic cataclysms. So the next time you hold a gold coin or admire a platinum watch, remember, you're holding something far older than Earth itself. Those atoms were born in a fiery collision billions of years ago, flung across the galaxy before becoming part of our planet's formation. They survived supernova, interstellar journeys, and even the chaotic early days of our solar system, all to end up here in your hands. Few things connect us more viscerally to the cosmos than realizing the jewelry we wear was once part of the most extreme events in the universe. The collision of two neutron stars is one of the most violent events in the universe, an explosive meeting so intense it distorts the very fabric of space-time. When these incredibly dense remnants of dead stars spiral toward each other, they don't just merge quietly. Instead, they unleash a kilonova, a flash of light and energy so powerful it outshines an entire galaxy for days. But what makes these rare cosmic encounters truly special isn't just their spectacle, it's what they leave behind. In the heart of that explosion, under pressures and temperatures beyond human comprehension, the heaviest elements in the universe are born. For decades, scientists puzzled over where elements like gold, platinum, and uranium came from. Supernova could explain some of them, but not all. Then, in 2017, everything changed. Astronomers detected gravitational waves rippling through space, a telltale sign of two neutron stars colliding over 100 million light-years away. But this wasn't just a ripple in space-time. Telescopes around the world swung into action, capturing the aftermath, a brilliant, rapidly fading glow rich with the fingerprints of heavy elements. For the first time, we had proof that kilonovae were cosmic forges, producing gold and platinum in quantities that dwarfed anything a supernova could create. The process is as precise as it is extreme. When neutron stars collide, they shred each other apart, flinging neutron-rich material into space at nearly the speed of light. In that chaotic maelstrom, atoms are bombarded with so many free neutrons that they grow heavier in seconds, a process called rapid neutron capture, or the R process. Ordinary fusion can't make elements this heavy. It takes the unimaginable violence of a kilonova to force atomic nuclei to absorb neutrons faster than they can decay. The result, a spray of precious metals, cosmic shrapnel sent hurtling through the galaxy to one day become part of new stars, planets, and even living things. What's astonishing is how much these collisions produce. A single kilonova can forge hundreds of Earth masses worth of gold and platinum in moments. The event detected in 2017 alone created an amount of gold equivalent to 10 times the weight of our entire planet. That means the ring on your finger, the circuitry in your phone, even the gold reserves in national banks. All of it likely originated in collisions like these, billions of years before our solar system formed. Yet kilonovae aren't just element factories, they're also cosmic messengers. The gravitational waves they produce allow us to measure the universe in ways light alone never could. By combining gravitational wave data with observations of the explosion's glow, astronomers can pinpoint distances across the cosmos with unprecedented accuracy. It's like the universe handed us a new ruler, one that stretches across billions of light years. These events remind us that the universe's most destructive moments are also its most creative. Without neutron star collisions, the periodic table would stop at iron, leaving our world devoid of the heavy elements that shape technology, medicine, and even life itself. Every time we mine gold from the earth or harness uranium for energy, we're tapping into the legacy of these ancient cosmic crashes, a reminder that even the rarest events in the universe can have the most lasting impact. Dark matter is one of the greatest unsolved puzzles in modern astronomy, an invisible substance that makes up about 85% of the universe's mass, yet refuses to interact with light or ordinary matter in any way we can directly detect. For decades, scientists have searched for its source, considering everything from undiscovered particles to primordial black holes. But here's a fascinating twist. Some researchers suspect that dead stars, particularly white dwarfs and neutron stars, might account for a fraction of this cosmic ghost. The idea isn't as far-fetched as it sounds. When stars die, they don't always vanish completely. White dwarfs, the dense cores left behind by sun-like stars, can linger for trillions of years, slowly cooling into cold, dark husks. Neutron stars, even more extreme, are so dense they could easily evade detection if they weren't emitting pulses of radiation. And if enough of these stellar remnants exist floating unseen between galaxies or lurking in the vast emptiness of intergalactic space, they could collectively contribute to the universe's missing mass. But there's a catch. For dead stars to explain dark matter, there would need to be far more of them than current observations suggest. The Milky Way alone would require a hidden population of white dwarfs or neutron stars numbering in the trillions, far exceeding the visible stellar graveyard we've catalogued. Some theories propose that an early generation of stars, born in the universe's chaotic infancy, could have produced a surplus of these remnants before fading into obscurity. Others speculate about exotic variants like strange stars, hypothetical neutron stars made of ultra-dense quark matter that might behave differently than ordinary stellar corpses. The challenge is proving any of this. Dark matter's gravitational effects are clear. It bends light around galaxies and holds clusters together like invisible glue. But pinning it down to specific objects, especially ones as elusive as cold white dwarfs or dark neutron stars, is like searching for shadows in a pitch-black room. Even the most sensitive telescopes struggle to spot these faint relics unless they're actively emitting light or interacting with their surroundings. Yet the possibility remains tantalizing. If even a small percentage of dark matter turned out to be tied to dead stars, it would reshape our understanding of cosmic history. It would mean that stellar remnants aren't just the endpoints of stellar evolution, they're active players in the universe's hidden architecture, shaping galaxies in ways we're only beginning to grasp. Until we have definitive answers, though, dark matter keeps its secrets close, reminding us that the universe still has mysteries even the brightest stars can't illuminate. The sun, our steady companion in the sky, won't shine forever. Right now, it's in the prime of its life, a middle-aged star fusing hydrogen into helium at its core, radiating energy that sustains every living thing on Earth. But in about 5 billion years, this familiar glow will change dramatically. As the sun exhausts its hydrogen fuel, its core will contract, heating up until the outer layers expand outward in a fiery transformation. The sun will swell into a red giant, its diameter stretching beyond the orbit of Mercury, then Venus, swallowing both worlds in a blazing embrace. What happens to Earth is still an open question. Some models suggest our planet might escape complete destruction, pushed outward by the sun's lost mass as it expands. But even if Earth isn't consumed, the conditions here will become unimaginably hostile. The sun's increased heat will scorch our atmosphere away, boil our oceans dry, and turn the surface into a molten wasteland. Any traces of life as we know it will have vanished long before the red giant reaches its maximum size. Yet this fiery expansion isn't the end of the sun's story. After billions of years as a red giant, it will shed its outer layers in a final, shimmering display, casting off a glowing shell of gas that will drift through space as a planetary nebula. At its heart, the sun's core will remain, a dense, Earth-sized ember known as a white dwarf. No longer fusing elements, it will glow faintly from residual heat, slowly cooling over trillions of years until it fades into darkness. This future might seem distant, but it's part of the same cosmic cycle that created us. The material in that future nebula, oxygen, carbon, nitrogen, was forged in the sun's core and will one day enrich the interstellar medium, just as past stars enriched the cloud that formed our solar system. New stars will ignite from these ashes, and with them, new planets. Some of those worlds might even harbor life, their chemistry built from the same atoms that once warmed Earth. The sun's fate is a reminder that even the most familiar things in the universe are temporary. Stars live, die, and recycle themselves, turning destruction into new beginnings. Long after our sun dims to a cinder, its legacy will continue, scattered across the galaxy in nebulae, new stars, and perhaps even new worlds yet to be born. Interstellar travel might sound like science fiction, but if humanity ever ventures beyond our solar system, dead stars could become our cosmic pit stops. Picture a spacecraft hurtling through the void, its trajectory carefully plotted to skim past a neutron star. The star's immense gravity would act like a slingshot, flinging the ship forward at speeds far beyond what our engines could achieve alone. This isn't just theoretical NASA. Voyager probes used similar gravity assists from Jupiter and Saturn to gain speed, proving the concept works. Now imagine scaling that up to the extreme environment of a neutron star, where gravity is billions of times stronger than Earth. A single pass could accelerate a ship to a significant fraction of light speed, cutting travel time between stars from millennia to mere decades. But gravity isn't the only resource these stellar remnants offer. Neutron stars and white dwarfs are also cosmic power plants, radiating energy that could recharge or even propel future vessels. A neutron star's magnetic field, for instance, is so intense it generates beams of radiation as it spins, energy that an advanced civilization might harness. Some theories suggest using these pulsar beams like interstellar lighthouses, not just for navigation but as power sources, tapping into their steady pulses the way we now harvest solar energy. White dwarfs, though less extreme, still glow with residual heat for billions of years, potentially offering a more stable energy source for long-term way stations. Of course, the challenges are as staggering as the opportunities. Approaching a neutron star is a deadly gamble. Its gravity would rip apart any ship that ventured too close, while its radiation would fry unprotected electronics and astronauts in an instant. Even white dwarfs, gentler by comparison, emit enough X-rays to pose serious risks. Future engineers would need shields far beyond today's technology, or ways to extract energy from a safe distance. And then there's the navigation problem. These objects are tiny by cosmic standards. A neutron star might be only 12 miles across, making them incredibly difficult to locate and target across light years of empty space. Yet the allure is undeniable. If we could master the dangers, dead stars might become the highways of the galaxy. Civilizations far older than ours could already be using them, their ships flickering past pulsars like cars refueling at cosmic gas stations. Some scientists even speculate that the precise timing of pulsar signals might one day reveal artificial patterns, evidence that we're not the first to dream of riding these gravitational waves. While these ideas remain speculative, they remind us that the universe is full of possibilities waiting to be explored. The same stellar corpses that once terrified ancient skywatchers could one day light the way for humanity's greatest journey, turning the relics of dead stars into beacons for the future. The cosmos has its own symphony, and pulsars are the universe's most precise metronomes. These spinning neutron stars don't just emit radiation, they pulse with clockwork regularity, some ticking hundreds of times per second with accuracy that makes Earth's atomic clock seem crude by comparison. When astronomers first detected these rhythmic signals in the late 1960s, the patterns were so unnervingly perfect that researchers jokingly labeled them little green men transmissions, wondering if they'd stumbled upon alien beacons. But the truth was even more astonishing. Nature had crafted its own celestial timekeepers, their steady beats cutting through the cosmic noise like a drummer keeping time for the galaxy. Scientists have found a way to translate these cosmic rhythms into something we can actually hear. By converting the radio pulses into audio frequencies, they've revealed an eerie interstellar soundtrack, a collection of whirs, clicks, and chimes that sound like something from a science fiction film. Some pulsars produce rapid, staccato beats resembling a hyperactive woodpecker, while others generate deeper, slower tones that evoke the bass notes of some enormous galactic organ. The Crab Nebula's pulsar, for instance, spins 30 times per second, creating a buzzing hum that would sit between the lowest notes of a piano and the rumble of a passing subway train. What makes these sounds even more fascinating is how they change over time. Young, energetic pulsars often have crisp, clear pulses, while older ones can sound slightly wobbly as their spin gradually slows. Some binary pulsars, those orbiting another star, produce Doppler-shifted melodies, their pitch rising and falling as they move toward and away from us. There's even a pulsar in the constellation Vulpecula that emits a dual-toned signal, creating an interstellar harmony as its two magnetic poles sweep past our line of sight. These aren't just cosmic curiosities, they're tools for understanding the universe. The precision of pulsar timing is so reliable that astronomers use it to test Einstein's theory of general relativity with exquisite accuracy. When gravitational waves pass through our region of space, they subtly alter the arrival times of pulsar signals, creating detectable ripples in the cosmic rhythm. Projects like the International Pulsar Timing Array are essentially turning the galaxy into a massive gravitational wave detector, using these dead stars as its sensors. There's something profoundly poetic about these celestial melodies. Long after their host stars exploded in violent supernova, these ultra-dense remnants continue to sing, their pulses carrying across light years with unwavering consistency. In a universe where chaos often reigns, pulsars stand as beacons of order. Their rhythmic beats a reminder that even in death, stars can create something beautiful. And as we listen to their otherworldly music, we're not just hearing the echoes of stellar collapse, we're tuning into the heartbeat of the cosmos itself. Long before telescopes revealed the true nature of dying stars, human cultures saw cosmic stories written in the night sky. Ancient Chinese astronomers recorded a guest star in 1054, what we now know as the Crab Nebula supernova, interpreting its sudden brilliance as an omen from the heavens. Halfway across the world, the ancestral Pueblones of North America may have depicted that same stellar explosion in petroglyphs, carving spirals and stars into rock faces as the sky blazed with light brighter than Venus. These weren't just observations, they were attempts to make sense of the unfathomable, to weave meaning from celestial violence. The Milky Way itself became a canvas for human imagination across civilizations. To the ancient Greeks, it was spilled milk from the goddess Hera's breast. Aboriginal Australians saw it as a river dividing the sky world, dotted with campfires of ancestral spirits. Norse mythology envisioned it as the ash tree Yggdrasil, its branches cradling the 9 realms. What's striking is how many cultures independently associated this stellar band with life-giving forces. Water, milk, the world tree, long before science revealed it truly was a nursery of stars, where stellar births and deaths continually reshape the cosmos. Even today, dead stars spark creativity at the intersection of science and art. Vincent van Gogh's Starry Night swirls with cosmic energy that eerily resembles modern images of turbulent nebulae. The pulsar's rhythmic radio pulses inspired the electronic beats of the Voyager Golden Record, carrying stellar music to potential extraterrestrial listeners. Science fiction writers from Arthur C. Clarke to Lou Sixon have imagined neutron stars as alien supercomputers or gravitational time machines, stretching known physics into speculative realms. There's something about these celestial remnants that captures our collective imagination, perhaps because they embody the ultimate paradox, where destruction and creation collide. Modern astronomers continue this storytelling tradition, just with different tools. When the Hubble telescope captures the Veil Nebula's delicate filaments, we're seeing the same stellar death that frightened or inspired ancient skywatchers. Only now, we understand it as a 3-dimensional structure expanding at 60 kilometers per second. Citizen science projects invite the public to classify pulsar signals, turning cosmic data into collaborative discovery. Even the names we give these objects, the Crab Nebula, the Black Widow Pulsar, the Hand of God Nebula, reveal our instinct to personify the cosmos, to find familiar shapes in the chaos of stellar wreckage. This enduring connection between dead stars and human culture speaks to something fundamental about our place in the universe. Whether carved in stone millennia ago or rendered in high-definition astrophysics simulations today, these celestial phenomena remind us that science doesn't erase wonder, it deepens it. The same supernova that once foretold empires' fates now teach us how atoms travel between stars. The Milky Way, once a mythological river, is understood as our galactic home, its stellar graveyards quietly recycling the elements that make our existence possible. In learning the true stories of these cosmic phenomena, we haven't lost their magic. We've discovered just how much more astonishing reality can be. Peering into the aftermath of stellar death requires more than just powerful telescopes. It demands an entire orchestra of instruments, each revealing a different piece of the cosmic puzzle. The Hubble Space Telescope, with its crystal-clear vision, captures the ghostly beauty of supernova remnants in visible light, their intricate filaments glowing like celestial lacework. But switch to the Chandra X-ray Observatory, and those same remnants transform into searing landscapes of million-degree gas, revealing the shockwaves still rippling through space centuries after the explosion. It's like viewing a painting first in gentle watercolors, then under ultraviolet light. Suddenly, hidden details leap out, telling a richer, more dynamic story. Gravitational wave detectors like LIGO and Virgo add another dimension entirely. These aren't telescopes in the traditional sense. They're more like cosmic microphones, listening for tremors in space-time itself. When 2 neutron stars collided in 2017, LIGO didn't just hear the crash. It measured the distortion of reality as the stars spiraled together, an event later confirmed by telescopes worldwide as a brilliant kilonova. This multi-messenger astronomy, combining light, gravitational waves, and even neutrinos, is like assembling a jigsaw puzzle where each piece comes from a different sensory realm. Suddenly, we're not just observers of stellar deaths, we're forensic scientists reconstructing cosmic crime scenes. Radio telescopes play a quieter but equally vital role. While optical images show the aftermath, radio waves pierce through dust clouds to reveal the hidden structures of pulsars and magnetars. The Very Large Array in New Mexico, for instance, has mapped the magnetic highways around neutron stars, showing how their intense fields channel particles at nearly light speed. Meanwhile, gamma-ray satellites like Fermi catch the universe's most energetic outbursts, magnetar flares so powerful they momentarily outshine the entire Milky Way. Each wavelength, from radio to gamma rays, exposes a different chapter in the life cycle of dead stars. What's truly revolutionary is how these tools work in concert. Hubble might spot a supernova remnant's delicate filaments. Chandra uncovers the searing gas within, and LIGO waits patiently for the next collision. Together, they've revealed how neutron stars are born, how they collide, and how their debris seeds the cosmos with heavy elements. Even amateur astronomers contribute, tracking the slow fade of supernova in distant galaxies, a reminder that decoding the universe's grandest explosions is a collective human endeavor. The next generation of instruments promises even deeper revelations. The James Webb Space Telescope's infrared eyes will peer through dust to study the chemistry of stellar graveyards. The upcoming Square Kilometre Array radio telescope will detect pulsars with unprecedented precision, potentially uncovering new physics in their spins. And future gravitational wave detectors in space, like LISA, could catch the mergers of supermassive black holes, events so colossal they make neutron star collisions look like firecrackers. These tools don't just show us dead stars, they connect us to them. Every photon captured, every gravitational ripple detected, is a message from across time and space, written in the language of stellar demise. And as our technological symphony grows more sophisticated, so too does our understanding of how destruction and creation dance together in the dark. Even the mightiest stars in the universe have their limits, boundaries set not by imagination, but by the unbreakable laws of physics. Take R136A1, for instance, a colossal star in the Tarantula Nebula weighing in at over 250 solar masses. For decades, astronomers debated whether such behemoths could exist, theorizing that radiation pressure from their own intense energy would tear them apart before reaching such sizes. Yet there they are, defying expectations, burning with the brightness of millions of suns. But these stellar giants don't get to shine forever. Their brilliance comes at a cost, an inevitable collapse so catastrophic it skips the usual stellar farewell and plunges straight into cosmic oblivion. The breaking point lies around 150 solar masses. Beyond this threshold, stars enter a realm where their own heat becomes their undoing. In normal stars, the outward push of radiation balances the inward pull of gravity, creating stability. But in these ultra-massive stars, something bizarre happens. At extreme temperatures, gamma rays in the core spontaneously transform into pairs of electrons and positrons, a process called pair instability. Suddenly, the radiation pressure drops like a failed support beam, and gravity gains the upper hand. The star's core collapses in on itself, triggering runaway fusion that doesn't just explode the star, but obliterates it completely. No supernova, no neutron star left behind. Just a black hole formed in the blink of an eye. These theoretical explosions, known as pair instability supernova, are thought to be the most powerful stellar detonations in the universe. A single event could outshine an entire galaxy for months, unleashing more energy than our sun will produce in its entire 10 billion-year lifetime. Some astronomers suspect they've already spotted the aftermath of such cataclysms. Superluminous supernova like SN 2007 BI, which blazed with unnatural intensity before fading away. Unlike regular supernova, these leave no compact remnant behind, just an expanding cloud of heavy elements and a void where a star once stood. What's truly fascinating is how these explosions shape cosmic evolution. A single pair instability supernova can forge and scatter enough iron to seed future generations of stars and planets. The first stars in the universe, composed of pure hydrogen and helium, may have met their end this way, exploding so violently that they jump-started the chemical enrichment of the cosmos. Without these early, massive stars and their dramatic deaths, the universe might never have developed the heavy elements necessary for rocky planets or life. Yet mysteries remain. No one has directly observed a star in the act of undergoing pair instability collapse, and the exact mass limits are still debated. Some models suggest stars could reach up to 300 solar masses before gravity overwhelms them, while others propose even higher thresholds under unique conditions. The recent discovery of stars like R136A1 pushes these boundaries, challenging our understanding of stellar physics. Every new observation peels back another layer, revealing just how extreme and how fleeting the lives of the universe's largest stars truly are. In the grand tapestry of cosmic evolution, these stellar titans are rare, fleeting brushstrokes here in a blaze of glory, gone in an instant, leaving behind only echoes in the form of black holes and enriched gas clouds. Their existence reminds us that even in the vastness of space, there are limits to growth, boundaries set not by the universe's willingness to accommodate, but by the fundamental laws that govern all things. And as we continue to search the skies for these cosmic giants, we're not just studying stars, we're probing the very edges of what's possible in nature. Quark stars represent one of the most tantalizing frontiers in astrophysics, a hypothetical state of matter so extreme it makes neutron stars seem almost ordinary. Picture the aftermath of a supernova so violent that even the neutrons in the collapsing core can't withstand the pressure. Instead of forming a neutron star, the unimaginable crush of gravity shatters protons and neutrons themselves, breaking them down into their fundamental building blocks, free quarks. This isn't just dense matter, it's matter stripped to its absolute limits. A swirling sea of subatomic particles behaving in ways that defy everything we know about the physics of solids. The concept emerges from a gap in our understanding of ultra-dense matter. Neutron stars already push atomic nuclei to the brink, with densities comparable to stuffing Mount Everest into a coffee mug. But quark stars would take this even further, reaching pressures so high that the boundary between individual particles blurs entirely. Instead of distinct neutrons packed together, you'd have a quark-gluon plasma, a primordial soup of quarks and the gluons that bind them, similar to the state of the universe mere microseconds after the Big Bang. Some theories suggest this quark matter could be strange, incorporating not just the usual up and down quarks found in normal matter, but also their exotic cousin, the strange quark, creating a stable yet utterly alien form of material. Why haven't we found one yet? The challenge lies in distinguishing quark stars from their neutron star cousins. Both would appear as compact, incredibly dense objects with powerful magnetic fields. But subtle differences might give quark stars away. They could be slightly smaller yet more massive than neutron stars of comparable size, or cool faster due to different heat transfer properties in quark matter. Some astronomers speculate that certain ultra-dense pulsars like XTJ1 739-285 with its puzzlingly high mass might actually be quark stars in disguise. Others look for unusual X-ray or gamma-ray emission patterns that could betray the presence of quark matter at their cores. The implications of discovering a quark star would reverberate far beyond astronomy. It would force us to rewrite textbooks on nuclear physics, proving that matter can exist in a stable state beyond atoms or even neutrons. It might shed light on quantum chromodynamics, the poorly understood rules governing how quarks interact, potentially revealing flaws or extensions to the standard model of particle physics. Some theories even suggest that quark stars could be the true source of fast radio bursts, those mysterious millisecond flashes of cosmic radio waves, with quark earthquakes releasing bursts of energy that ripple across the universe. Until we have definitive proof, quark stars remain a beautiful hypothetical, a reminder that the universe still holds phenomena wilder than our boldest theories. They challenge us to look deeper, to question whether neutron stars are truly the final state of collapsed matter, or if somewhere in the cosmos, objects even stranger are waiting to be discovered. Whether they exist or not, the mere possibility expands our imagination of what's possible when stars die, pushing the boundaries of both matter and our understanding of reality itself. The universe, in its grand expanse, operates on an unyielding principal entropy, the slow but inevitable march toward disorder. Over trillions of years, this relentless process will shape the fate of all stars, galaxies, and even the fabric of space itself. Picture a future so distant that all the stars we see today have long since burned out. The Milky Way, now a graveyard of stellar remnants, drifts in a sea of darkness where new stars no longer ignite. White dwarfs, those fading embers of sun-like stars, will have cooled into black dwarfs, cold, dense spheres of crystallized carbon, invisible against the void. Neutron stars, once pulsating with incredible energy, will have spun down into silence, their magnetic fields decayed, their light extinguished. Only black holes remain, their event horizons the last markers of a universe that once teemed with light. This is the heat death of the universe, a state of maximum entropy where all usable energy has been exhausted, and no more work can be done. Temperatures will approach absolute zero, and the cosmos will settle into a uniform, featureless expanse. Yet even in this frozen twilight, the remnants of dead stars persist not as sources of warmth or life, but as relics of a more vibrant past. Black holes, the final keepers of mass and information, will slowly evaporate over incomprehensible timescales through Hawking radiation, releasing their energy in faint quantum whispers. The last visible structures in the universe, they too will vanish, leaving behind only a diffuse sea of photons and elementary particles, stretched to infinite wavelengths by the relentless expansion of space. But there's a haunting beauty in this inevitability. The iron cores of dead stars, the gold forged in neutron star collisions, the carbon that once fueled life, all of it remains scattered across the void. Though no living thing will witness it, these atoms endure as the universe's final testament to its own history. The remnants of supernova that once illuminated the night skies of Earth will still drift unchanged, their stories locked in the stillness of eternity. This cosmic epilogue isn't just a tale of endings, it's a reminder of scale. The lifespan of a star, even a galaxy, is but a flicker against the vast timeline of the universe. Yet in that fleeting moment, stars create the conditions for planets, chemistry, and life. The heat death may be inevitable, but the legacy of stellar death is written into the fabric of reality itself. Every atom in our bodies, every element on Earth, carries the echo of stars that lived and died billions of years ago. Long after the last light fades, that legacy remains a silent, eternal monument to the universe's capacity for creation, even in the face of its own dissolution. Imagine a world where the sun isn't a warm, yellow star but a rapidly spinning corpse, a pulsar blasting its surroundings with lethal radiation. Yet against all odds, life clings to existence here, sheltered in deep caves or beneath miles of ice, adapting to an environment we'd consider unsurvivable. This isn't science fiction, it's a real possibility astronomers are now exploring. The discovery of planets orbiting pulsars like PSRB 1257+12 shattered the notion that habitable zones only exist around stable, sun-like stars. These pulsar planets bathed in deadly X-rays and gravitational tides shouldn't exist, and yet they do, raising the electrifying question: if life can emerge on Earth, why not here? White dwarfs, the faded remnants of stars like our Sun, offer another twist in the search for extraterrestrial life. At first glance, these cooling embers seem unlikely hosts. Their habitable zones would be so close that any orbiting planet would be tidally locked, one side perpetually scorched, the other frozen. But recent simulations suggest otherwise. A planet with a thick atmosphere could redistribute heat, creating a narrow band of temperate conditions along the twilight line between day and night. Even more intriguing, white dwarfs are stable for billions of years, far longer than the Sun's main sequence lifetime, giving life ample time to arise and evolve. Some researchers speculate that civilizations advanced enough to survive their star's red giant phase might even migrate inward, transforming white dwarf systems into cosmic oases long after their star's death. The real revelation here isn't just about location, it's about resilience. On Earth, extremophiles thrive in boiling hydrothermal vents, acidic lakes, and even the radioactive wreckage of Chernobyl. If life can adapt to such harsh conditions here, why not on a planet illuminated by a pulsar's rhythmic fury or a white dwarf's dim glow? The energy sources would be radically different: tidal heating replacing sunlight, or bioluminescence harnessing particle showers from a magnetar's magnetic field. But the principle remains: life finds a way. This changes everything in our search for cosmic neighbors. Instead of focusing solely on Earth-like planets, we might need to broaden our horizons to include the universe's most extreme real estate. Future telescopes could scan the atmospheres of pulsar planets for traces of industrial pollution, a telltale sign of civilization clinging to survival. Or we might detect artificial megastructures orbiting white dwarfs, harvesting their residual heat. The universe's habitability could be far vaster and far weirder than we ever imagined. So while these environments seem hostile beyond measure, they remind us that life is tenacious. The same stellar deaths that create black holes and neutron stars might also, against all odds, cradle new possibilities for existence. And if life can persist in the ashes of dead stars, then perhaps we're not alone, just surrounded by neighbors stranger than our wildest dreams. Mining a neutron star sounds like science fiction, an idea ripped from the pages of an interstellar heist novel. Yet as Earth's reserves of precious metals dwindle and our appetite for technology grows, the allure of these cosmic gold mines becomes harder to ignore. Picture a teaspoon of neutron star material, compressed so densely it weighs 1 billion tons, packed with more platinum and gold than humanity has ever mined. The potential is staggering, but so are the obstacles. To even approach one, we'd need spacecraft capable of surviving radiation levels that would vaporize modern electronics, not to mention gravitational forces strong enough to spaghettify a human in milliseconds. And that's before considering how to extract anything from an object with a surface gravity 100 billion times stronger than Earth's. Beyond the technical nightmares lie deeper ethical dilemmas. Neutron stars aren't just lifeless rocks, they're the tombstones of massive stars, often playing critical roles in their galactic neighborhoods. Some act as cosmic lighthouses, their precise pulses guiding astronomers in mapping the universe's structure. Others, like magnetars, generate magnetic fields that shape interstellar gas clouds, influencing star formation light years away. Disrupting these remnants could have unintended ripple effects, altering regions of space we don't yet fully understand. There's also the philosophical question: do we have the right to exploit stellar graves? If future civilizations view neutron stars as sacred relics, or even as historical archives holding clues to the universe's evolution, mining them might be seen as an act of cosmic vandalism. Then there's the sustainability paradox. The very metals that make neutron stars so valuable were created through cataclysmic violence, collisions and explosions that scattered these elements across the galaxy. Harvesting them en masse could disrupt the natural recycling process that's been running for billions of years. Unlike asteroid mining, which retrieves materials already adrift in space, extracting from neutron stars would require dismantling objects that are still dynamically active. It's the difference between collecting fallen branches and chopping down ancient redwoods. Yet the debate isn't entirely one-sided. Proponents argue that advanced civilizations must grow beyond their home planets to survive, and accessing neutron star resources could unlock technologies we can't yet imagine. The gold in a single neutron star collision could build Dyson swarms to power interstellar travel or fund research to reverse climate change. Some even suggest that leaving such resources untouched is the greater ethical failing, a waste of potential that could benefit trillions of future beings. What's clear is that this isn't a challenge for our century or even the next, but the conversation forces us to confront bigger questions. How should humanity interact with the cosmos? Are we destined to be caretakers or conquerors? The answers might shape not just our future among the stars, but our understanding of what it means to be a civilization worthy of them. Standing beneath a starry sky, it's easy to feel small, not just in space, but in time. The light reaching your eyes tonight may have left its star centuries ago, while others traveled for millennia before finally meeting your gaze. Dead stars amplify this humbling truth. The universe operates on timescales that dwarf human existence entirely. Take white dwarfs, the fading embers of sun-like stars. These stellar remnants will glow faintly for trillions of years, longer than the current age of the universe itself. To put that in perspective, if the lifespan of a white dwarf were compressed into a single year, all of recorded human history would occupy less than a millisecond. Yet here's the paradox: our fleeting existence grants us a front-row seat to cosmic wonders that the universe itself will one day forget. In billions of years, the last stars will flicker out, leaving behind a dark expanse where no one witnesses supernova or marvels at pulsars. We live in a privileged epoch, a sliver of cosmic time when stars still shine, when black holes actively shape galaxies, and when the afterglow of stellar deaths remains visible to curious observers. The very act of studying a supernova remnant connects us across impossible gulfs of time. When you examine the Crab Nebula's twisting filaments through a telescope, you're seeing light emitted before the Norman conquest of England, a celestial message sent centuries ago, just now reaching its destination. This awareness transforms how we perceive our place in the cosmos. The iron in your blood, forged in a star's final moments, links you to events older than Earth itself. Your ability to comprehend that connection, to trace atoms back to their stellar origins, is a triumph against cosmic indifference. Long after our civilization fades, the light from dying stars will continue its journey through the void, carrying stories of creation and destruction to distant galaxies. But for now, in this brief window where minds exist to interpret them, those stories have meaning. We are the universe's way of bearing witness to its own grandeur, fleeting participants in an endless cycle that began long before us and will continue long after. Perhaps that's the greatest gift dead stars offer, not just wonder but perspective. They remind us that time isn't merely something we measure in minutes or years. It's the canvas on which the universe paints its most spectacular works. And though our brushstrokes on that canvas may be small, they're no less significant for their brevity. After all, it only takes a moment of clarity to grasp eternity. There's a profound elegance in the way the universe transforms endings into beginnings. When a massive star exhausts its fuel and collapses in a supernova, the explosion isn't just a finale. It's a sculptor's chisel, carving shockwaves through interstellar clouds and triggering the birth of new stars. The same blast that tears a star apart also seeds the cosmos with heavy elements, scattering them like cosmic confetti. Picture the Veil Nebula, its delicate filaments glowing in hues of red and blue, not just wreckage but a masterpiece painted by stellar death. These remnants are more than graveyards, they're nurseries where destruction and creation dance in perfect balance. Neutron stars take this paradox even further. Born from the most violent collapses, they become laboratories for physics-defying imagination. A single teaspoon of their material weighs 1 billion tons, yet they spin with such precision they rival atomic clocks. Their magnetic fields could strip atoms apart from thousands of miles away, yet their steady pulses guide astronomers like celestial lighthouses. These extreme objects don't just test the laws of nature, they rewrite them, proving that even in chaos, the universe finds order. Then there are white dwarfs, the quiet poets of stellar demise. Unlike their explosive counterparts, they fade gently, exhaling their outer layers into space as glowing planetary nebulae. The Cat's Eye Nebula, with its intricate concentric rings, or the Butterfly Nebula's symmetrical wings, these aren't random shapes. They're the star's final sonnet, written in light and gas, each curve and filament a stanza in a cosmic elegy. And within those expelled layers lies oxygen, carbon, nitrogen, the very elements that will one day form planets, oceans, and perhaps life itself. This interplay of violence and beauty isn't just astronomy, it's alchemy on a galactic scale. The gold in a wedding ring, the iron in our blood, the calcium in our bones, all were forged in the hearts of dying stars, then scattered across the void to become part of us. Every atom in your body heavier than hydrogen is borrowed stardust, on loan from events that occurred billions of years ago. The universe doesn't waste a single speck of matter. It recycles, transforms, and repurposes, turning destruction into the raw materials for new wonders. So when we gaze at a supernova remnant or a pulsar's rhythmic flicker, we're not just observing death, we're witnessing rebirth. The same forces that obliterate stars also craft the building blocks of existence, weaving a story where endings are never final, and every loss plants the seeds for something new. In the grand tapestry of the cosmos, destruction and creation aren't opposites, they're partners, locked in an endless waltz that paints the universe with light, energy, and life. From the cataclysmic fury of supernova to the slow, shimmering fade of planetary nebulae, the death of a star is never truly an end, it's a transformation. These celestial final acts aren't just spectacular light shows, they're the universe's way of reinventing itself. When a massive star collapses, the explosion doesn't just vanish into the void, it becomes the architect of new solar systems, scattering heavy elements like cosmic breadcrumbs for future planets and life to follow. The gold in your jewelry, the iron in your blood, even the oxygen filling your lungs right now, all of it was forged in these stellar crucibles, billions of years before Earth existed. But the story doesn't stop with creation. Dead stars continue shaping the cosmos long after their light fades. Pulsar beams slice through galaxies like interstellar lighthouses, their precise rhythms helping astronomers map the universe's darkest corners. White dwarfs, those fading embers of sun-like stars, enrich surrounding gas clouds with carbon and oxygen, the very elements that make life possible. And black holes, the most enigmatic remnants of all, govern the motion of entire galaxies from their invisible thrones. Far from being cosmic graveyards, these stellar ghosts are active participants in the universe's ongoing evolution. This grand cycle of destruction and rebirth mirrors deeper truths about existence itself. Just as forests need wildfires to clear the way for new growth, the universe requires stellar deaths to create the complexity we see today. The first stars lived and died in solitude, leaving behind a cosmos devoid of planets or life. But their sacrifice, the metals forged in their cores and scattered by their explosions, made everything after possible. We are literally made from the ashes of those ancient giants, walking testaments to the universe's boundless creativity. So the next time you gaze at the night sky, remember, you're not just looking at distant points of light. You're witnessing an ongoing story of resurrection written across billions of years. The same forces that obliterate stars also crafted the building blocks of your being. That connection isn't poetic license, it's scientific fact, written into every atom of your body. And as we continue to unravel these cosmic mysteries, we're not just exploring the universe, we're discovering our own origins, one stellar ghost at a time. If this journey through the life and death of stars sparked your curiosity, hit that like button and subscribe for more deep dives into the cosmos. Drop a comment below, tell us which stellar remnant fascinates you most, or share your own cosmic wonderings. Until our next adventure among the stars, keep looking up. The universe has countless more stories to tell, and you're already